Right now, science may be facing one of its biggest crises in over 100 years. For a long time, astronomers have relied on a single master model to explain the universe. It's the framework that tells us how fast space is stretching, how old everything is, and how it all began. But when astrophysicist Adam Rees, a Nobel Prize winner, pointed the James Webb Space Telescope deep into space, something strange showed up. Far away in the oldest corners of the cosmos, Webb found a clue that could shake the foundations of modern cosmology. It showed that the universe is stretching apart faster than the standard model says it should. If that's true, then one of the most basic ideas we have about space itself might be broken. For the first time in decades, the math that describes the universe doesn't line up with what we're actually seeing. Rees and his team are now saying openly that the old model might not be telling the full story. Somewhere out there, something invisible seems to be pushing the universe to expand faster than expected, and nobody knows what it is. If this turns out to be real, we may know about the universe's age, its past, and even how it will end. But that's only part of the problem. Webb's other discoveries suggest we've misunderstood how the universe works on a much deeper level. It has spotted the earliest ancestors of supermassive black holes, objects that formed in ways nobody predicted. It has caught violent bursts of energy tearing apart galaxies before they even had a chance to grow up. And most recently, while looking at a strange visitor passing through our own solar system, an object called 3-Obki Atlas, Webb picked up something no telescope had ever managed to see before. So what exactly is going on? Why does the universe seem to be breaking its own rules? And could the true ending of the universe be far stranger and far darker than anyone imagined? Let's go back to the late 1920s. American astronomer Edwin Hubble was working at the Mount Wilson Observatory when he noticed something odd. Distant galaxies weren't just sitting still, they were rushing away from each other, and the farther apart, two galaxies were, the faster they moved apart. Something unseen was stretching the very fabric of space. That was the moment we first understood that most of our universe is hidden from us. Here's a way to picture it. If you shrunk the entire universe down to the size of a house, everything we can see or touch or measure, every grain of sand, every planet, every star, would fit into a single small room. Everything else in that house would be pitch black, locked away behind laws of physics we still don't fully understand. But scientists kept digging. A century later, researchers like Vera Rubin, Saul Perlmutter, and Brian Schmidt, along with massive projects like the Planck satellite mission and NASA's WMAP observatory, built a new picture of the cosmos, and it looks more like an unsolved puzzle than a finished model. Everything we can actually see, stars, planets, us, makes up only about 5% of everything that exists. The other 95% is a total mystery. Around 27% is dark matter, an invisible substance that acts like glue holding galaxies together. The remaining 68% is dark energy, a mysterious force baked into space itself that keeps pushing the universe to expand. Scientists set out to nail down one specific number, how fast this force is pulling everything apart. They call it the Hubble constant. To measure it, they came up with two completely different approaches. The first approach looks into the deep past. It was carried out using the Planck Space Telescope, which studied the cosmic microwave background, the oldest light in existence. This faint glow is the leftover heat from the Big Bang itself, light that has been traveling for 13.8 billion years. Planck didn't look at galaxies directly. Instead, it mapped the entire sky in microwave wavelengths, creating an incredibly detailed picture of tiny temperature differences in this ancient light, almost like a fingerprint of the baby universe. Each of these tiny variations marks where galaxies would eventually form, spots where matter and gravity were already clumping together. Scientists then took this pattern and compared it to a mathematical model of the universe, one where gravity, the amount of matter, and dark energy are all plugged in as known values. They adjusted the model bit by bit until it matched what Planck actually observed. Once it matched, the model spit out a number, the current rate of cosmic expansion. The answer came out to roughly 67 kilometers per second for every megaparsec. A megaparsec is about 3.26 million light years. So for every extra megaparsec of distance between two galaxies, they're moving apart about 67 kilometers per second faster. Two galaxies, 2 megaparsecs apart, would already be separating at 134 kilometers per second. And it only grows from there. The second approach looks at the present, right here, right now. Scientists measure the expansion rate using something called the cosmic distance ladder, a chain of measurements where each rung depends on the one before it. Adam Rees, who leads the JWST project, played a huge role in refining this method, turning it into one of the most reliable tools in cosmology today. Researchers start by finding special pulsing stars in nearby galaxies called Cepheid variables. These stars are unusual because there's a direct predictable link between how fast they pulse and how bright they truly are. That makes them useful as cosmic yardsticks or standard candles. The idea is simple. If you know a star's true brightness and compare it to how dim it looks from Earth, you can calculate exactly how far away it is. From there, the ladder keeps climbing. Cepheids let scientists calibrate the brightness of type Ia supernovae, which are even more powerful cosmic beacons, visible across enormous distances. That's how researchers measure the expansion of the observable universe using nearby present-day data. For years, this work relied on the Hubble Space Telescope, and its results were surprising. About 73 to 74 kilometers per second per megaparsec, roughly 8 to 9% higher than the number from the cosmic microwave background. At first glance, an 8 or 9% gap might not sound like much. But in cosmology, it's enormous. Picture two doctors weighing the same person. One says 154 pounds, the other says almost 168 pounds. Both scales are properly calibrated, both methods are well tested. At that point, the issue isn't the numbers themselves, it's figuring out why two trustworthy methods are telling two different stories. That's exactly the situation cosmologists are stuck in today. Two solid methods, two different answers, and no clear explanation. They call this puzzle the Hubble tension. For a while, researchers, including Rees himself, hoped the problem was just old equipment. Maybe the aging Hubble telescope was introducing some small error. All eyes turned to the James Webb Space Telescope to settle the debate. With its huge gold-coated mirror and extremely sensitive infrared instruments, Webb can cut through cosmic dust and pick out individual stars with incredible precision. NASA pointed it at the exact same galaxies and the exact same Cepheid stars that Hubble had already studied. Everyone expected Webb to find the mistake and fix the discrepancy. Instead, the results published between 2023 and 2024 turned the whole situation upside down. Webb found no errors in Hubble's data. It confirmed precisely that the local measurements were correct, and that the real expansion rate is that higher number, around 73 to 74 kilometers per second per megaparsec. The instruments were fine all along. That 9% gap is real, and it has turned the Hubble constant into a full-blown crisis for cosmology. It suggests the universe isn't expanding the way Einstein's theory of relativity, baked into the Standard Model, predicts it should. Something fundamental is missing from our understanding. And the more scientists try to reconcile these two numbers into one clean answer, the more it looks like the real problem goes beyond just the expansion rate. It touches something even more basic, time itself. According to the Standard Model built on Planck's data, the universe is about 13.8 billion years old. But if Rees's local measurements are correct, and the true expansion rate really is closer to 73 or 74, then the universe could actually be up to 1 billion years younger than we thought. That gap might sound small on a human scale, but cosmically speaking, it hints that the entire story of how the universe evolved might have unfolded differently than the version we currently accept as fact. And if we've gotten the past wrong, it raises an unsettling question. Do we actually understand where this is all heading? Cosmologists like Katie Mack, one of the leading voices in cosmology and particle physics, argue that if dark energy keeps dominating the universe the way it appears to now, the most likely ending is something called heat death. And it might be the coldest, loneliest ending physics allows. Over tens of billions, then trillions of years, space keeps stretching. Galaxies vanish one by one past the cosmic horizon, permanently losing contact with each other. Light leaving one galaxy will simply never reach another. Stars burn out, one after another, and no new ones take their place. The once bright universe fades into an endless, silent darkness, with a few scattered clumps of matter, separated by unimaginable emptiness. Space becomes so thin and stretched out that even two atoms bumping into each other becomes a rare, almost impossible event. That would be the end of everything. Time itself would stop meaning anything, because there would be nothing left for it to measure. To really understand where the universe is headed, we have to look back at where it started. And when we study the early universe, we need to be ready to find things that don't fit inside our current scientific playbook at all. During one of its deep space surveys, the James Webb Space Telescope captured light that had been traveling toward us for more than 13 billion years, a signal from a time when the universe was only a few hundred million years old. In just one image, Webb captured roughly 45,000 galaxies scattered across the depths of time, with the tiniest specks representing baby protogalaxies just beginning to form. As scientists studied this image closely, they noticed something odd about a group of these galaxies. Their light was shifted heavily toward the red end of the spectrum, meaning it had stretched out enormously on its long journey to us, a sign of how incredibly far away and how incredibly old these objects really are. NASA researchers estimate they already existed just 600 million years after the Big Bang, but what really caught the attention of researchers Seiji Fujimoto and his colleagues was something else entirely. These objects were far brighter than they had any right to be for something that young. The obvious guess would be that these were simply the very first galaxies, young, a bit messy, and cranking out stars at a rapid pace. But that explanation didn't hold up. Building a galaxy takes time. Gas has to cool down, collapse under its own gravity, and go through multiple rounds of star formation. That's a slow process. Yet, these red objects were already shining brightly at a point when barely any time had passed since the Big Bang. Their estimated mass made things even stranger, on average, hundreds of millions of times the mass of our Sun. So we're looking at something extremely bright, extremely heavy, and shaped like a galaxy, but existing at a moment in cosmic history when galaxies like this simply shouldn't have had time to form. Digging deeper, a research team that included Spanish astrophysicist Pablo Arrabal Haro found something even stranger in the light coming from one of these objects, nicknamed the Egg, Glimpse 75. Instead of traveling straight out into space, the light appeared to be bouncing around inside the object before escaping. Arrabal Haro and his team think this happens because the object is wrapped in an incredibly thick shell of partly ionized gas and cosmic dust, thousands of times denser than what you'd find in a typical galaxy. As light tries to escape, it keeps getting scattered inside that shell, bouncing around instead of shooting straight out. This led the team to a striking hypothesis. Hidden underneath all that gas might be the most dangerous kind of object in the entire universe, a quasar. Picture an enormous black hole, something like Gargantua from the movie Interstellar. Then multiply its power many times over. That's essentially what a quasar is, the blazing, hyperactive core of a young galaxy, where a supermassive black hole is devouring nearby matter at an insane rate. Whatever it can't swallow spirals around it, forming a massive disk of material that gets whipped up to nearly the speed of light. Friction heats that gas to millions of degrees, and the result is an object that can outshine an entire galaxy of 1 billion stars. Quasars are both the most massive and the brightest single objects in the universe, even from 2.5 billion light-years. To keep churning out new stars, a young galaxy needs one key ingredient: cold hydrogen gas. In the early universe, that raw material was everywhere, so you'd expect these young galaxies to keep thriving for fuel supply with no way to get it back. Based on the current rate of gas loss, researchers estimate this galaxy could effectively die within about 50 million years. And keep in mind, we're seeing this play out with a 12.8 billion year delay, like watching an old recording. By now, that galaxy may already be long gone or completely transformed, but from our point of view, its present hasn't happened yet, because the light simply hasn't had time to reach us. Sometimes, though, the strangeness doesn't come from billions of light years away. It comes from something passing right by our own solar system. You probably remember the buzz around 3I Atlas, the mysterious object that entered our solar system from somewhere else entirely. Recently, Webb detected something on this object that no telescope had ever picked up before. Right now, 3I Atlas is roughly 900 million miles from Earth, having already passed through the inner solar system, and currently moving past the orbit of Saturn. By the early 2030s, it will completely leave our solar system, crossing the heliopause, the boundary where the sun's solar wind can no longer reach, and begin its journey through interstellar space. This summer in 2026, using its mid-infrared instrument, Webb detected methane on an interstellar object for the very first time ever. That caught astronomers off guard. Methane is a highly volatile gas that should have boiled away long before this object got anywhere near the sun. Somehow, this visitor managed to hold on to it. For billions of years, methane ice sat locked deep beneath the comet's surface, shielded from radiation. Only once the sun's heat finally reached that core did those hidden pockets activate, sending powerful jets of gas erupting from inside the comet. Webb's data revealed unusual ratios too, far more methane and carbon dioxide than you'd find in any comet native to our own solar system. Based on these measurements, researchers estimate this chunk of ice may have formed somewhere between 10 and 12 billion years ago. If that's accurate, the star system where it originally formed might not even exist anymore. It's wild to think that we're getting a look at a comet that could be nearly as old as 87% of the universe itself. For scientists, 3I Atlas is basically a time capsule, and it's already shown us that chemistry in other star systems doesn't necessarily follow the same rules as our own. When this interstellar visitor made its closest pass by Earth in December 2025, the internet briefly lost its mind, with people seriously worrying about some kind of doomsday scenario. In reality, its path was always safely far from Earth. The same can't quite be said, though, for another object with an actual calculated chance of colliding with the Moon, or even Earth in 2032, an asteroid called 2024 YR4. Astronomers sometimes call objects like this city killers. Scientific estimates put this particular rock at roughly 200 feet across, about the size of a 15-story building. That might not sound huge on a cosmic scale, but its destructive potential is massive. A direct hit could wipe out an entire city, leaving behind nothing but a massive crater and scorched ruins where a community used to be. Earlier models had already flagged an unusually high risk of it hitting the moon in 2032, around 4.3%, a record at the time for this kind of prediction. Then, the asteroid disappeared behind the sun's glare, making it impossible for ground-based telescopes and radar to track. Scientists expected they'd have to wait until 2038 for another good look, once it swung back around and became visible again. But this past March, Webb managed to track the asteroid anyway. Sitting at the L2 point, about 930,000 miles from Earth, Webb picked up the asteroid's faint heat signature, effectively seeing right through the sun's glare that was blinding everything else. It captured this on February 26, 2026. In the resulting image, the asteroid shows up highlighted in green, with a red line marking its calculated path. Spotting something this small was already tough, and its extremely low brightness made it even harder. NASA researchers pointed out, almost jokingly, that the asteroid reflects about as much light as an almond would if you placed that almond at the distance of the moon, roughly 1 billion times fainter than the dimmest stars you can see with the naked eye. That gives you a sense of just how sensitive Webb's instruments really are. This new data cleared up all the remaining uncertainty and corrected earlier calculation errors. The updated orbital model gave a much clearer answer. On December 22, 2032, asteroid 2024 YR4 will pass about 13,200 miles from the moon. The risk of any kind of global disaster has officially dropped to zero,